Hello everyone, my name is Huang Siyun. Today I will present my project on limits of multivariable functions, focusing on the epsilon-delta definition for functions from Rn to Rm. I will first introduce multivariable limits, then explain the epsilon-delta definition, prove the uniqueness theorem, and finally discuss its connection with continuity. Let's start with something familiar. In single-variable calculus, when we say the limit of the function as x approaches x0 equals v, it means that when x gets closer and closer to x0, fx gets closer and closer to v. That's pretty simple, right? But in multivariable functions, our input becomes a vector, such as xy. Here's the tricky part. In one dimension, you can only approach x0 from either the left side or the right side. But in higher dimensions, you can come from any direction, from above, below, diagonally, or even along a curve. So the question becomes, how do we define a limit when there are infinitely many directions to approach a point? That's what we are going to talk about today. So how do we make this idea precise? The first thing we need is a way to measure distance. In 1D space, distance is just the absolute value. But in higher dimensions, we use something called the Euclidean norm. You have probably seen it before. It's just the usual length of a vector. For example, the distance between 2 points x and x0 is simply the length of the vector x minus x0. And similarly, in the output space, the distance between fx and a vector v is the norm of fx minus v. Why do we care about these notions? Because once we have a clear way to talk about closeness in both the input and output spaces, we can finally extend the definition of a limit from one variable to multi-variables. So now let's go to the formal definition. Here is the famous epsilon-delta definition. We say that the limit of fx as x approaches x0 equals v if the following condition holds. For every epsilon greater than 0, there exists a delta greater than 0, such that whenever x is within delta of x0, but not equal to x0, the value of fx is within epsilon of v. The key idea is that no matter how small an output tolerance epsilon is chosen, we can always find an input tolerance delta that guarantees the condition. Let's visualize what's actually happening here. On the left, we have the input space. We draw a small delta ball around x0. On the right, we have the output space. We draw a small epsilon ball around v. The definition states that every point inside the delta ball on the left is mapped into the epsilon ball on the right via the function f. So we can think of it like a guarantee. If you stay close enough to x0 in input, I promise you will land close enough to v in the output. This works no matter how small the epsilon is. That's what makes this definition so powerful. Now, let's go to a very simple example. Consider the function x squared plus y squared. You might recognize this. It's a paraboloid, like a smooth bowl shape. We want to show that the limit at the origin is 0. Intuitively, let's look at the picture. If you walk down towards the bottom of the ball, the height goes to 0. But let's prove it using the epsilon-delta definition. Here's the key observation. The absolute value of fxy, which is just x squared plus y squared, is exactly the square of the distance from xy to the origin. So if we want fxy to be less than epsilon, we just need the distance from xy to the origin to be less than the square root of epsilon. So we simply choose delta to be equal to the square root of the epsilon. Let's check. When the distance from xy to 0, 0 is less than delta, then x squared plus y squared is less than delta squared, which is epsilon. So we are done. We have found our delta. So the limit exists and equals 0. Now, we have seen what the limit definition looks like and how it works in practice. But here's an important question. If a limit exists, can it have two different values? Let's find out. The uniqueness theorem states that if a limit exists, then it must be unique. Now you might be thinking, well, of course it can't have two different values. That's very obvious. You are right intuitively. It is obvious. But in mathematics, obvious is not good enough. We need to prove it. So let's see how the definition possesses the uniqueness. The idea of the proof is using contradiction. Here is the setup. Suppose that the function has two different limits, call them u and v. Since they are different, the distance between them must be positive. Now, here is the key idea. Let's look at the picture. Around both u and v, we draw balls with radius epsilon. If both u and v are truly limits of the function, then fx must lie inside both two balls whenever x is sufficiently close to x0. So when the two balls do not overlap, like this, the fx cannot belong to both of them at the same time. This will create a contradiction. So we just need to choose epsilon small enough so that the two balls are completely separated. But how small it is? Notice that when the two balls will just touch each other, the epsilon is just half of the distance between u and v. So if we choose a smaller value, such as 1/3 of the distance, then the two balls must be completely disjoint. Now let's go to the main proof. We start by assuming, for contradiction, that u is not equal to v. Because both u and v are limits, then Epsilon-delta definition gives us delta 1 and delta 2 that works for any epsilon. Choose epsilon to be 1/3 of the distance between u and v. That's what we have discussed before. Let delta to be the minimum of delta 1 and delta 2. Why do we use minimum? Because we want to make sure that both limit conditions hold at the same time. If x is within delta of x0, then it's definitely within both delta 1 and delta 2. Now we have a delta that works for both limits at the same time. So we know fx is within epsilon of both u and v. We use the triangle inequality, get the distance between u and v is less than 2/3 of the distance between u and v. That's impossible. A number cannot be strictly less than 2/3 of itself. Therefore, our assumption was wrong. U and v cannot be different, so the limit must be unique. So why do we care about this theorem? The uniqueness theorem guarantees that a limit, if it exists, has only one value. Without this, continuity would not make sense. Imagine a function approaching two different limits near the same point. What would continuous mean? It would be a mess. But because we know limits are well defined, we can now confidently define continuity, and then differentiability, and then all the powerful tools of calculus, like optimization, modeling, physics, and engineering. And that brings us to continuity. We have the definition for continuity. A function is continuous at x0 if the limit of fx as x approaches x0 equals the function value at x0. There's no jump, no sudden break. Now, here's the key point. Let's look at the definition. We find that it is exactly the epsilon-delta definition we already wrote down. And because we already proved that the limits are unique, continuity is well defined. The result forms the foundation for any further topics in calculus and analysis. Then comes to the end of my presentation. We have covered a lot today. So let me summarize what have we actually learned. We introduced the Euclidean norm, discussed the geometric interpretation of limits, proved the uniqueness theorem, and saw how limits are related to continuity. The epsilon-delta definition isn't just about some abstract definition. It's the rigorous foundation of multivariable analysis. It works in any dimension, 2D, 3D, or 100D. It allows us to build calculus on solid ground. Here is the resources I used for this project. Thank you for listening. I'm happy to answer any question.